Hi everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today we're going to do problem 6.3, which is about 1,1,1-trichloroethane. This is when you look this up in Wikipedia, this is the structure you get because they don't show you the hydrogens over here, so it's kind of a funky looking thing. But anyway, that's 1,1,1-trichloroethane. And you're being asked a deceptively simple question. If you go into the Arctic and you measure and you have 0.9 milligrams per liter of this stuff in the air and 2.5 milligrams per liter in the water, is it at equilibrium, or is it volatilizing out of or volatilizing into or absorbing into the Arctic Ocean? And you're asked at two temperatures, 0 and 10 degrees Celsius. So a couple things going on here. First, I want you to notice that the salinity is given as 0.35 parts per thousand. And if you would want to convert that into molarity, which is what you're eventually going to need to use the Seshanow equation, you could go and Google convert salinity in parts per thousand to molarity, and 3 hours later you'd still be deeply confused about how to do this. I am not an oceanographer, so I'm going to give you the simple explanation here, which is it's complicated. Converting parts per thousand to molarity is complicated because the density of the seawater is changing. You know, the density of seawater is not 1 gram per cubic centimeter like everything else in the world. So anyway, the short answer is it's 0.5 molar. Just trust me, seawater is 0.5 molar. The Seshanow equation is not sensitive enough to have it really matter whether it's 0.51 or 0.49 molar. So trust me, it's 0.5 molar. So anyway, to answer this question, one of the first things you want to do is figure out what is the Henry's law constant of 1,1,1-trichloroethane. So now let us do that using our friend EpiWin. Okay, so here's EpiWin. This is the first menu you get when you open it up. We could go here to HenryWin, and this is here's the little thing that pops up. I usually just do the name lookup, trichloroethane. Got a couple of options here, but here's 1,1,1-trichloroethane. Hit calculate. And so first of all, one nice thing it does is give you a structure. That's always lovely. The other thing it does is it shows you a bunch of different numbers here. So there is an experimental Henry's law constant here. And as I've always said in this class, if you have an experimental value, you should use it. You know, there's no point in driving yourself crazy with all these estimation techniques if someone has taken the time to actually measure these things. So you should probably use the experimental value. But notice that there's a couple of different ways to estimate it. Here's the bond contribution method and the group contribution method. And the take-home messages, they give you different answers. Okay, so here the measured value, 1.6 times 10 to the minus 2 atmosphere meter cube per mole. Here's 4.2 times 10 to the minus 3 atmosphere meter cube per mole. And then here's 1.6 times 10 to the minus 2. So this estimated value is fitting very, very well with the experimental value, but this one, not so much. And the really, hilarious part of this is that depending on which of these Henry's law constants you decide to use, you're going to get a different answer. You're going to get a different answer as to whether this compound is volatilizing or absorbing into the Arctic Ocean. Yay! I love chemistry, don't you? All right, so I'm going to use this value. This is the log Henry's law constant that you get from the back of the book. Okay, and it's not immediately obvious. You have to kind of dig for this information. But the Henry's law constants that are given in the back of the book are dimensionless. So this is the log of the Henry's law constant, and so if we take 10 to that value, we get a Henry's law constant of 1.41 dimensionless. Again, depending on which value you use, you might get a different answer for this problem. But the math is the same, so just kind of trust me on this. Okay, now, so you have a Henry's law constant, but again, this is at 25 degrees Celsius. I need to know what this Henry's law constant is at 0 and 10 degrees Celsius, and also at a different salinity. So, we need to figure out delta H of Henry's law for this compound. So by looking at table 6.3, we can see that the delta H for the Henry's law constant for many compounds is basically the same as their delta H of vaporization, right? So if we knew delta H of vaporization, we wouldn't need to do much to it. We could just use it directly as the delta H for Henry's law. And just to prove this to you, here is table 6.3. Sorry, a little bit too big. Table 6.3, and again, for this is a small molecule, 1,1,1-trichloroethane, so, you know, down here with the small molecules, and delta H of vaporization is very similar to delta H AW for these compounds. Okay, so if I knew delta H of vaporization, I could just, you know, declare victory and depart the field. Okay, so a couple different ways to get that. Here I'm going to use Trouton's rule. You could do that. And so the Trouton's rule, you have to know the boiling point. You can look that up in the appendix. You use the Kistiakowsky equation here to back out delta S of vaporization. Comes out to be 85 joules per mole Kelvin. That's what we expect from Trouton's rule. Should be around 85, somewhere around there, 88, something like that, joules per mole Kelvin. And since you know that, and you know that delta G at the boiling point is equal to 0, which is equal to delta H of vaporization minus the boiling point times T delta S, that lets you calculate that the delta H of vaporization of this compound is 30 kilojoules per mole, and that's reasonable. You know, here's some values of delta H of vaporization for some small molecules, and you know they're in the range. So you know that you have a reasonable value. Again, from comparison to table 6.3. So. Once you have it, and there, you know, there's other ways to do this. You could also use the Gauss-Schwarzenbach equation. You know, there's different ways to do this. But once we have that number, then we are able to convert our Henry's law constant for temperature using this equation here. And notice that it does not matter whether we do the salinity correction first and then do temperature, or we do temperature first and then do salinity. It doesn't matter mathematically, comes out the same thing. So we're going to do temperature first. Remember that if we're doing the delta H for Henry's law, we need to think a little bit about the units of our Henry's law constant. You can't use this equation if you have dimensionless units on your Henry's law constant. So there's a couple different ways to do this. What I've done in this spreadsheet is converted my dimensionless Henry's law constant to having some units of liter atmosphere per mole Kelvin here. So here's my R value, my temperature, and that leads me from my dimensionless Henry's law constant into one that has dimensions of liter atmosphere per mole Kelvin. So then I can take the natural log of this and push it into this equation. So here's the natural log of my Henry's law constant at temperature 1, and then here's my Henry's law. There's the Henry's law constant. It's actually the natural log of Henry's law constant. Make this a little bit bigger. Nope, still not big enough. Bigger, bigger, more. Okay, here we go. Boom. Okay, so here's the natural log of the Henry's law constant at temperature 1 plus, then here's delta H AW divided by R times the difference in the reciprocal temperatures, right? And again, remember, you have to have your delta H vaporization here has to be in joules per mole, not kilojoules per mole, if you're going to use R in 8.314 joules per mole, which is what we're using here. So we have to make sure we get the units right. But there's your equation. So there's your natural log of Henry's law constant at 2 degrees Celsius. Let's make that little again. Okay, and then you just take the EXP of it right here, and that gives you your Henry's law constant in liter atmosphere per mole. And then you're going to convert it back to dimensionless units, because that's what I need, because the concentrations I was given are in milligrams per cubic meter. And so I divide one by the other, I lose my units, I need dimensionless units on my Henry's law constant. So I get 0.52. Okay, that's at 0 degrees Celsius. I do exactly the same thing for 10 degrees Celsius, and I get 0.79 as my dimensionless Henry's law constant. Now I have to correct these for salt. And so this, you actually have a Sechnow constant for this specific chemical from table 5.7. That's the one that lists all the Sechnow constants. The Sechnow constant for this chemical is 0.25. So here's your Sechnow equation. Again, we know that seawater is 0.5 molar. So you apply your Sechnow equation here. Again, I'll make this wider so you can see it better. So you're taking B54, which is the Henry's law constant at 0 degrees, times 10 to the value of 0.25, which is the Sechnow coefficient, times the molar salt concentration of 0.5. And lo and behold, your Henry's law constant is now 0.69. So it went from 0.52 to 0.69. And then at 10 degrees, it goes from 0.79 to 1.1. So the Henry's law constant is going up. Okay? And you can do the math here. I'm going to make this wider so you can see it. 10 to the 0.25 times 0.5 here is 1.33333, so it's increasing the Henry's log constant by about 33% due to the salinity in the ocean water. Okay, so again, that's salinity in ocean water. Usually in the normal course of things in the environment, you're not going to have a salinity much greater than that, unless you're dealing with some weird sort of brine system. But usually that's as high as you're going to go, and 0.25 is a pretty reasonable value of the Sessionow constant. So this increase of 33% is about as big an increase as you're going to get, unless you're dealing with a brine. Okay. So here's your your Henry's log constant, having already been adjusted for both temperature and salinity. And so then, if I use my concentration in the water of 0.25 milligrams per liter here, and I predict what would be in the air if it was at equilibrium with that, I get 1.7 milligrams per liter at 0 degrees and 2.6 milligrams per cubic meter, at 10 degrees Celsius. Okay, and then we compare that by what we actually measured. What we actually measured was 0.9. So these predicted values are higher. So in order to come to equilibrium, the air concentration has to be higher. Okay, so that means that the TCE, the TCA, the 1,1,1-trichloroethane, has to be volatilizing out of the water column in order to move toward equilibrium. Okay, the other way to do that is to calculate the ratio of sea air to seawater. That's the 0.9 divided by 2.5, and you get 3.6 and 0.36. 0.36 is less than both of these Henry's law constants. So at both temperatures, it means that the chemical has to be volatilizing out of the water column. Okay, because this ratio is less than the Henry's law constant. And since Henry's law constant is concentration in air over concentration in water, this fugacity ratio, this is what we call the fugacity ratio. This fugacity ratio has to go up. And since this fugacity ratio is sea air over seawater, in order to get it to go up, sea air has to go up. Okay, so that's telling you that this compound is volatilizing out of the water column at both of these temperatures. Okay, so that's how you employ Henry's law constant. Think about fugacity ratios, adjust for temperature, and also adjust for salinity.